So to move on to talk about some of the current trends in small satellite design, this is a mission that we have flying in orbit at the moment. It's called TechDemoSat, and some of the things that we're actually trying out for the first time on this mission are listed on the left-hand side of the slide. The space industry is inherently quite conservative. It would prefer not to put new technologies onto a mission and fly it on an operational satellite for the first time. It's generally preferred to demonstrate that a satellite technology works before it's baselined for an operational mission. And this is the purpose of a mission like TDS-1. We are putting various pieces of electronics onto the spacecraft and testing them for the first time in the space environment. And some of the technologies that we're flying would be described as satellite platform technologies. So they would be part of the bus of the spacecraft. That would include elements of the avionics like gyros, star trackers, very small sun sensors would fall into that category. Then we're also looking at new payload capabilities. So on the top of the illustration of the satellite is a panel that is a prototype radar transmitter that will form part of a mission called NovaSAR that I'll be talking about in a minute. We also have an experiment on the front of this spacecraft, which is using GPS reflectometry to generate sea state data. What the antenna does is pick up GPS signals that are reflected off the surface of the ocean. In the process of reflection, the sea state imposes a Doppler shift onto the signal, and so we can use a passive system to measure sea state from low Earth orbit. In the lower right of this slide is a drag sail experiment which has yet to be deployed, but at the end of the satellite mission we will deploy this drag sail to increase the area of the spacecraft. That means that it will see more drag from the upper end of the Earth's atmosphere, and as a result what we will hope is that the satellite will lose energy from its orbit, spiral in and burn up in the Earth's atmosphere harmlessly within 25 years, which is the emerging international standard for getting your hardware out of orbit without contributing to the debris problem. This slide shows a couple of small satellites that we are developing in the CubeSat class. So these are really very small spacecraft indeed, weighing just a few kilograms. The first one is on orbit. It's based around a Google Nexus mobile phone, and it's a 3U CubeSat, so its dimensions are 30 centimeters by 10 by 10. And the satellite mobile phone has many of the functions that you need to operate the spacecraft. It has inertial sensors to work out which way it's pointing. It has GPS on board to determine its orbit, for example. Where we want to go in the future with experiments like this is to have a pair of such satellites able to use the proximity sensors from games consoles to do rendezvous and docking, and the idea is to actually bolt two of these CubeSats together in orbit autonomously in the future, with the aim of enabling us to build much larger structures in orbit autonomously, launching various elements of a bigger spacecraft on separate launch vehicles. I'd like to move from talking about practical experiments to invite you to consider a thought experiment, which by analogy perhaps will show how we go about thinking about some of our spacecraft design. So I'd like you to imagine that there's an unexpected sound source behind you in the room. Your natural reaction, if you heard a strange noise, would be to turn your head to see what the funny noise is. And that's an example of your ears, which are a 360-degree omnidirectional sensor capable of geolocating a sound to an accuracy of about 5 degrees. Putting your eye in the right place, the central field of acuity of the eye, is also about 5 degrees, and that's not a coincidence. Your ears will put your eye in the right place. But that isn't the only thing that your eyes are able to do. Your eyes have a central 5-degree field of acuity, but you also have peripheral vision, which is essentially a change detection and area coverage capability, which extends out to about 60 degrees either side. You can demonstrate how important that peripheral vision is if you put together a pair of joke glasses, which is something that I've done in the past. What you need to do is take something like a drinking straw, cut it down to about that sort of length, which gives you a 5-degree field of view, and stick it to the center of a pair of glasses, and then blank out the rest of the optical field of view using a piece of card. What you discover when you wear a pair of glasses like that is you can still read quite happily off a piece of paper held in front of you, because you've still got the in-focus central 5-degree field of acuity. What you realize that you've lost when you're wearing those glasses is if you try and move around a room, you've lost the cueing information that your peripheral vision provides you with. So you tend to try and waggle your head from side to side in order to give yourself the area coverage rate that you've been denied by the piece of card. And it becomes very apparent how inefficiently you use your central 5-degree field of view if it's not cued appropriately. And so having different types of sensor on a spacecraft is rather like having ears and different functions from your eyes if you're a human being. So these two spacecraft illustrated on this slide have different types of sensor. They both have wide area cameras that provide relatively low resolution imagery, perhaps 20-meter resolution on the ground, over a very wide swath of, say, 600 kilometers. So they're rather like your peripheral vision. Both satellites also have a relatively high resolution camera on them that allow them to do the narrow field of view of the eye, if you like. They collect data over a few kilometers at a much higher spatial resolution. And you could conceive of a satellite like this also having some sort of radio frequency receiver, might be referred to as signals intelligence or SIGINT capability, which would act like the ears of a spacecraft too. So this is an example of one of those satellites and how its capabilities derive from having different types of sensor. So Nigeria Sat-2 is a mission that was launched a little while ago, and this is one of the images taken during its checkout phase of Salt Lake City Airport in the United States. The image has some interesting features. There is an aircraft making an approach into landing, and that is actually visible in this image. The reason that the aircraft appears as a multicolour feature in this image is because at the back end of the detector in the camera there are multiple detectors operating at different wave bands. So there are detectors operating at red, green, blue and near infrared, and each of those detectors is swept across the ground by the satellite at a very slightly different time. As a result, the aircraft, which is moving rapidly through the scene, is imaged in a very slightly different location by each of the detectors. So when you combine the data from the different detectors into a single image, you get a multicolored version of the aircraft in the scene, which appears like a little rainbow. That is very much like the sort of change detection capability of your eye. It's a particular signature that allows you to pick up a moving target within a scene. Another advantage of having multiple sensors on a spacecraft is that you can achieve what is rather like a zoom function, although unlike a zoom on a camera where you physically change the focal length of the system. What we're demonstrating with this particular series of images is the ability to provide wide area context and then zoom in on a particular area of interest. The area of interest that we chose for this demonstration was Port Stanley Harbour in the Falkland Islands. We imaged the area with the wide area sensors on the satellites, so you start off with a 300 kilometre swath in this case, and we also used the high resolution camera to take an image of the centre of the field centred on Port Stanley Harbour itself. So what I'm going to show you now is a series of images as we effectively zoom in or show smaller elements of the images in succession. So starting off, we have the whole of East Falkland, and then we can zoom in progressively until we get to a point where you can see Port Stanley Harbour in the wide area imagery, and you might consider, if you stare carefully enough, that you might be able to convince yourself there are some ships moored in Port Stanley Harbour. But if you try and zoom any further with this particular image, it starts to pixelate and look rather unattractive. So at this point you switch to the high resolution image, and I think in this image you can convince yourself quite easily that there are a number of ships moored up in the harbour. And if you then continue to zoom in on the high resolution image, you get to the point where you can see the individual ships in the harbour, most of which are at anchor, but it's quite easy to identify in this image one of the ships in motion because it's leaving a wake behind it. If you look very carefully, you can see that these ships have a cruciform structure. They each have a boom sticking out on either side, and that is a particular fishing technique that's used to try and catch squid. So this is the South Korean squid catching fleet moored up in Port Stanley Harbour. If you move into the multispectral domain and exploit the colour data available from the sensors, you can potentially do even more in terms of wide area maritime surveillance. This example is roughly 30-metre resolution data of Singapore Strait, and it's a false colour multispectral image where we've combined the data from the red, green and near infrared sensors on the satellite into a single image. However, if you go back to the original data sets where the detectors on the satellite are working in the separate colour bands, you can do some interesting things. On the left-hand side is the original data that comes down from the satellite, and on the right is where we've inverted the data and enhanced the contrast a little. In the green band, as you might expect, the ocean is obviously a bluey-green colour. You can actually see the currents and the motion of the water. So if what you're interested in is ocean currents or potentially the places where you may be getting plankton blooms and hence fish, you would want to look in the green band. Alternatively, you might choose to work in the near-infrared band, because in the near-infrared the ocean surface itself is extremely uniform and the ships sat on the surface have a very significant contrast to the water that they're sitting on. So if your task is to detect ships, it would appear that the near-infrared band data is what you would want to use. You might even want to move into the mid-wave infrared. This is data taken from a rather older satellite, again with a resolution of about 20 meters. operating in the mid-wave 3 to 5 micron band in the infrared. This is actually an image of Gibraltar. The dark smudges on this image are some of the clouds that habitually form above Gibraltar as the air is forced up and over the rock. A characteristic cloud that's called the Cap of Gibraltar tends to form. And you can see that in this image. You can see ships, you can see the wakes of ships, and over on the right hand side of Gibraltar you're actually seeing partway through the water column, you're actually getting some bathymetry data. You're actually able to penetrate the water column to some degree and see features underneath the surface, which may also be of interest. Talked so far about optical images, but we're also working on a radar satellite mission, as I mentioned when I was talking about the TechDemoSat-1 mission. The satellite that we're hoping to derive from the knowledge that we gain from TechDemoSat-1 is illustrated here. It's a small satellite radar with an antenna that measures 3 meters by 1 meter, and we're hoping to get a variety of modes at different resolutions and different areas on the surface of the Earth. We haven't flown the antenna in space yet, but we have flown a prototype on an aircraft to demonstrate that we can create imagery, and what's shown at the bottom left is an image generated by the synthetic aperture radar flown on the aircraft, and shown adjacent to it is an optical image for comparison. As part of the testing campaign, we flew the aircraft over Langstone Harbour near Portsmouth, and this is one of the imagery, some of the imagery that we generated as a result. What you may notice is a series of bright points that are located in the river channel, and you might initially assume that those are the small fiberglass boats that are moored up in Langstone Harbour. If you thought that, you'd almost be correct. At the wavelengths that we're using in the S-band, the radio waves essentially pass straight through the hulls of the ship, straight through the fiberglass, where they then encounter the water surface. And if you can picture the shape of the water surface underneath a small boat, the concave depression that's created in the water by the hull of the boat actually creates a reflective surface that acts a little bit like a mirror and concentrates the radar energy back to the receiver. So what you're actually seeing with these bright points are the holes in the water made by the boats in Langstone Harbour. There are a whole variety of different processing options that you can do with a radar, and one of the things that we're quite excited about exploring with the NovaSAR mission is the ability to process different hands of polarization in order to generate different data sets. Some of the images on the screen here exploit the fact that you can transmit horizontally polarized data and receive horizontally polarized reflections. You can transmit vertical polarization and receive vertical, and you can also do one of the cross products, either transmit horizontal and receive vertical, or vice versa. That gives you 3 unique data sets which you can then combine into essentially color radar imagery. A lot of radar data that's been collected in the past hasn't had this ability to exploit polarization, so you've had a monochrome radar image. But as you can see from the examples here, if you are able to use polarimetry, you can generate data where different crop types and different vegetation types come out in different colors, and indeed the difference between man-made structures, which tend to have flat surfaces and so have a different polarimetric signature to the vegetation, are quite apparent. You can see the difference between man-made objects and natural vegetation quite easily